Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my great pleasure to have Professor Le Song. Le is currently an assistant professor at the Department of Computer Science and Engineering, School of Computing, Georgia Institute of Technology. He obtained his PhD in computer science from University of Sydney in 2008, and then he conducted his postdoc research at the School of Computer Science, Carnegie Mellon University from 2008 to 2011. His basic research interests include non-parametric and coding methods, probabilistic graphical models, and dynamics of network process, and also its applications. He received an MNIST Career Award in 2014. Please.
Okay. Thanks for everyone for coming. Okay. And I'm going to talk about kernel methods and how to make it scalable to millions of data points, or even tens of millions of data points. So the motivation for this work is we try to catch up deep learning with the kernel methods. Okay. The kind of motivating problem is this gigantic image classification problem. You have millions of labeled examples, and then the number of classes is also very big. So 1,000 classes is just a subset of the classes. There's even more. And then what we want to do is to take this image and then predict its labels. The label can be just mushroom, things like this. And then what is shown here are the labels predicted by some algorithms. You might predict the top 5 labels. And then some label has high probability. Okay? So you see this prediction is actually provided by neural nets. And it's doing a pretty good job. Sometimes when the correct label is not in the top places, but it might be in the second place, for instance, like this. So the best performing algorithm I mentioned is the deep neural nets. So it's a very complicated model. It has multiple layers. But the layers are structured in such a way that you see patterns. In the first 5 layers, it's this convolution pooling layer, highly structured processing unit. I'm going to explain a little bit more. And then in the next 2 layers is going to be these fully connected layers, and then trying to perform some kind of nonlinear transformations. In the last layer is going to be this multiclass logistic regression. So what is in this convolution max pooling layer? It's performing some very simple operations. So essentially, the convolution layer is just taking some convolution kernel that's different from the positive semi-definite kernel I'm going to talk about, but it's also called kernel. So you take these small templates, and you have some number to it. Essentially, you perform weighted sum over your original image and move this window across the entire image. You produce another image. And then very often in neural nets, you also apply this operation max after you finish the convolution. That's called rectified linear units. You also perform nonlinear threshold type of thing, okay? After you perform this convolution. So essentially, the first 5 layers are performing this type of operations. You convolve the image with some templates, and you perform that nonlinear operation, and also do max pooling. I'm going to explain. So the max pooling is something even simpler. It's essentially reducing the resolution of image, and you just take a small patch and look at the value in this small patch, and you just return the maximum value in that small patch. That's the operation. By that operation, typically, you reduce the resolution of image. You interleave between this convolution and max pooling for many layers, 5 layers, and it's the best performing model. And then after that, you have 2 layers of these fully connected layers. So it is just taking the input image or vector and perform the weighted combination of everything in that image, and then you produce an output pixel. So you also apply these max rectified linear units, this operation. So you do it twice in a hierarchical fashion. So it's highly mysterious, right? And then afterwards, you put the logistic regression on top of it. So essentially, you try to learn this weights W. So you do a weighted combination of the input vectors. And then and you push it through some exponential function that gives you something related to the probability of predicting label Y. Okay? So this is the model. And then,
Sorry.
Yeah.
So can you explain just again this max pooling operation? What
Right. So max pooling operation is just take a small patch in your original image, and then just return the maximum value in that small patch, and then fill it in as a new pixel.
And so you were saying that I'm doing convolution and then max pooling?
Yeah, you might interleave between them. Yeah.
So when you say interleave, you mean that one layer is doing
So
convolution?
max pooling together, supposedly. Yeah. So one layer, I mean that the convolution and max pooling, convolution followed by max pooling. Yeah. Sometimes they may skip this step, so by model selection or whatever. I don't know why. Okay. So it's such a highly structured model doing lots of max, okay? And then in the end, you push it through this multi-layers of this multi-class logistic regression. So it's highly structured, okay? And different layer has different function. But the goal of this model is to do this gigantic nonlinear classification task. And this is just a detail about the model, the parameter. So when you have a convolution, you need to specify these filters, kernels, right? And this is the way to sort of specify those parameters using convolution, max pooling, things like this. You have this original image, which is 224 by 224 and 3 color channels, okay? So the size, the kernel size is going to be 7 by 7. So you slide across this image, and then you might jump, rather than sliding window, but you jump too, okay? And then you use 96 of them. You get an image of 110 by 110 and 96 after the first layer of convolution. And you do max pooling, you reduce the spatial resolution. You get something like a 55 by 55 by pulling in a 3 by 3 window. So that's how they specify this model. And then you do convolution again, 5 by 5 window, stripe 2, and use 256 of them, you get a smaller image. You do max pooling, convolution, again, convolution, convolution. Okay, here they skip this max pooling operation. And here is another convolution and max pooling, and pushes through fully connected layer, and fully connected layer, and then multi-class logistic regression. Okay? So if you look at this very complicated model, the convolution actually, it consists of 5 layers, but the total number of parameters in that convolution layer is only 3.7 million parameters. Majority of the parameter actually lies in the last 3 layers for this fully connected layer and the multi-class logistic regression, and it's 58 million parameters. So essentially, given this gigantic image data set, you want to learn all these 60 million parameters, okay? Okay, that's the problem, yeah?
Do you happen to know how they came up with these magical numbers, y?
So actually, they have a nice package. You can just specify the configuration for all these layers.
No,
and it's
how did they came up?
I think
7 by 7 and not
model selection.
9.
I think model selection over 10 years or maybe 20 years. That's my impression. Yeah, you can experiment with this configuration, by specifying a small configuration file. They can just search for this architecture.
Try and error.
Yeah. I think try and error. But this convolution makes sense in some sense, extracting image feature. I don't quite understand the fully connected layer. I understand this multi-class logistic regression. So we all try to understand when we put all these things together, what's going to happen, right? Why is it doing so well? Yeah. So we try to understand. Yeah.
You have the 3 to 96, 256. That's the number of filters, because the number of filters you use.
Yeah, number of filters, 96 filters. That's why you get something image like 96 colors. Yeah.
Okay, basically you reduce the size of the image, but you increase the number of
Yeah,
filters.
that's right.
Okay.
Yeah. So when you do convolution, for instance, in this layer, 5 by 5 filter, it can work across different color channels. So you simultaneously look across 96 dimension, different color channels. So it's something like this. Yeah. So they managed to get it working, okay, and then working so nicely. When you try to learn these parameters, the algorithm that has been used is very simple. The driving horse behind this is really this stochastic gradient descent. You take a small batch of data, you compute a gradient, and you use the chain rule of derivative, and you get update for all these parameters. Yeah, you have a gigantic non-convex optimization problem, You just take the gradient of the objective with respect to parameter and use the chain rule to update it. But when you try to chain it, you also generate something called the virtual images. You are not just using the original data set of 1.3 million data points. You actually generate some image by randomly crop the image or mirror image, something like this. Do some transformation of the image. Generate something like the original data set, but slightly different. Okay? So along the way, the original data set is 1.3 million. You actually generate up to 100 million data points. And it takes a week in GPU to train this model. You get this performance. If you predict the top one label, use the top one label, and then compare to the actual label, and then the error is like 42%. Okay, that's the top one classification error. Yeah.
So why there is a sudden jump between?
Yeah. So I've explained in this point the manual adjustment of learning rate. The way they do it is they set this learning rate to be some constant, and then after some point they see these test error curve, it flattens and you drop the learning rate, and then it has a sudden decrease in the error, and then after some point it flattens, you decrease until after 3 of this adjustment. You don't see any improvement anymore, okay? So this is something that if you don't try it, you won't realize it, how they actually train it, okay? Yeah. Basically.
How they manually adjust?
So you just watch this curve. you can basically estimate this, the change, I guess, okay? If you want to do it automatically, yeah.
What's the training error for couple file?
The chaining error is going to be like a 30 or 20. Yeah, there's a huge overfitting there.
I mean, technical error for couple file.
Top 5, nowadays, the best performing model can be below 10%. It's very accurate. It's close to human judgment already, okay? So this is the state of this model. And then actually for this model, it creates a lot of unsolved questions as well. Of course, it performs so well in many applications, speech, image. The question is this very special kind of architecture. Maybe there's some special characteristic in the data which is particularly suitable for this type of architecture. It's not clear what kind of assumption you can make about the data such that this processing pipeline is really good. So I haven't seen any principle, the theoretical work for this question. So, and also Wi-Fi layer convolution max pooling, can we use other architecture operations to extract these features? It's not clear, yeah, whether there's any alternative and simpler operation which you can also use. And then, of course, why 3-layer fully connected nonlinear units? Yeah, why do you need these nonlinear transformations? Why not 4? And is there a way to do it in a shallow fashion? And can you use alternative nonlinear classifiers if you just wanted the nonlinear classification? So in this talk, I'm going to essentially explore these questions. I'm also very interested in the top 2, but now I don't have anything concrete for the top 2. So I'm going to use kernel method, trying to explore these 2 questions a little bit. I'm going to try to replace these 3 layers, fully connected nonlinear units, and the multiclass logistic regression by kernel methods, and see whether I'm able to achieve a comparable result. If I'm able to do that, maybe this 3-layer is not necessary. Okay, you can just replace it by a traditional nonlinear non-parametric method. And what's maybe really useful is this convolution max pooling layers. Okay. Yeah. Okay. So essentially, the kernel method, I mean, is this type of kernel, positive semi-definite kernel. When you have, it's essentially a function taking 2 arguments. So if you have a data set of fixed size m, you make this kernel matrix. That matrix has to be positive semi-definite. Okay, it's this special type of kernel. It's different from the smoothing kernel from statistics. It's different from this convolution kernel. It's this type of function, kernel function. So essentially, I'm going to estimate some, nonlinear classification functions, right? I'm trying to do multi-class nonlinear classification. I'm going to restrict my classification function to be in this space of function, the space of function spanned by these kernels. Okay, I fix one argument. I chase out the class of function using these data points from a particular space. So when I have this positive semi-independent kernel, the nice property is the kernel function itself is going to lie in that space. And then the inner product between two kernel functions is going to give you this kernel value. And then if you have a function in that space, and then you can evaluate that function by just performing inner products. That space has some nice property on it. For instance, some familiar kernel functions are polynomial kernels. So this kernel is definitely not in the smoothing kernel family. And the Gaussian kernel is also a smoothing kernel in the statistics literature. So essentially, for this particular kernel function, if you have a function in that space, which is a linear combination of this kernel, you will get a function of this shape. For instance, you can represent highly nonlinear functions just by linear combination of kernel sits on each individual data points. Okay? So this is just a brief introduction of this type of kernel function, the space of function chased out by these kernels. And then in Duty, you can think about this kernel method as transforming the data. For instance, here is a binary classification problem. You have negative class and positive class. You want to do nonlinear classification. This kernel function is going to transform this data to a new space, potentially infinite dimensional space. In that space, you try to find linear relationship in that space. Okay? So many kernel method has this intuition behind, and many kernel method actually can formulate it as an optimization problem, trying to find some function f in that space. You minimize some kind of expected loss. L is the loss function. You have some data x and y. Y can be the label generated from some distribution. You try to minimize this expected loss function and subject to some constraint that the norm of that function in the RKHS is bounded. So an equivalent formulation of this top optimization problem is you move the constraints to the objective function and add this mu is something like a regularization parameter. Okay? The beta and mu is related. So you can choose very different loss function. You get different algorithms. Kernel logistic regression, if you choose this loss function, you get support vector machine, you get logistic regression here. Okay? So this is so you typically, for kernel method, you solve it in the dual. So essentially, you use this so-called representative theorem. You have n data points. You replace the expected loss by this empirical loss. And then it turns out the solution of the optimization problem is going to have a form like this. It's just weighted combination over the kernel function applied on the training data points. Or you are optimizing over some function in function space. Could be infinite dimensional. Okay? So if you have that representative theorem, you can, in principle, plug in that into the original optimization problem, and then just optimize over this alpha instead. Okay, alpha is in some Rm. Sorry, it's not f. Okay, it's just some finite number of alpha. Okay. So you solve this optimization problem, but the problem is if you observe it carefully, you have this kind of double sum in the objective function. That means for each pair of data points, you have to evaluate this kernel function. Okay, and that creates lots of problems. Okay, think about m is 1 million. So if you want to evaluate pairwise kernel function, and essentially you need to fill in the entries in this big matrix, and then 1 million by 1 million, you cost this memory, 10 to the 12. And the computation is generally m squared d. D is the dimension of the original data. Okay? So it's huge. So you have to come up with a way to scale this kernel method up. So there has a lot of effort already. For instance, some approach based on low-rank decomposition of this kernel matrix. So you take this kernel matrix, you don't compute this entry. You have a way to incrementally approximate this kernel matrix by some low-rank factors. So this method, either Nice-Jones method in complete stochastic decomposition, many other methods. Usually the computation of this method is going to be linear in the data point, t squared in the rank you choose, and d the dimension of data. And the storage is going to just mt. So, but if you look at the generalization ability, after you do this low-rank approximation, plug into your optimization algorithm, and you get your function, you look at the generalization ability, the best you can prove without any further assumption is the generalization ability comparing the expected loss produced by this best function in the family, and the function produced by this low-rank decomposition. And then the generalization ability is the difference is going to be 1 over square root t, the rank, plus 1 over square root the number of data points. If you want to get best out of your data, you have to match these two terms, essentially. And that means that the t has to be the order of m. So you get n cubic kind of computation here, and then you get n square memory consumption again. Okay? So essentially, if you actually in practice, you also find this is the problem. So you do some low-rank decomposition fixed to some small rank. You find that you learn the classifier always loses some performance comparing to the case where you optimize directly with respect to this full Kernel matrix. That's what you observed. Because in theory, you need to match these two terms up. Okay? Recently, people are more looking into this so-called random feature approximation of the kernel function. So essentially, there's some interesting relationship between this kernel function, positive semi-definite kernel function, and some random processes. Essentially, if you have this kernel function, you can always express it as some kind of integral form. Okay? You will have some random variable omega. It follows some distribution p. And then this kernel function can be written as some random function which is indexed by this omega. Apply on your x, and the random function apply on x pi. You do this type of L2 inner product look thing with respect to this omega. Okay? So you can also write it as this expected form. Okay? So for some of the kernel function, you can find this distribution p omega in closed form. You can find this phi omega in closed form. But you can also go from this direction to that direction. If you can pick whatever nonlinear function, phi, omega, random feature you want it. You can pick some distribution you want it. And then you just define kernel this way. It's going to give you a valid positive semi-definite kernel. Okay? So you can go both directions. But people has worked out some closed form expression for some well-known kernel functions. For instance, for Gaussian Navier kernel, suppose the form is like this. Delta is the difference between x and x pi. The random function phi omega is just going to be something like cosine omega transpose times x plus tau, and omega follows Gaussian distribution, and tau follows uniform distribution. Okay. Actually, uniform distribution between I think 0 to pi, something like that. Okay. And then if you have another kernel, Laplace distribution, any family of translation kernel, you have some nice solution. Yeah? The corresponding distribution over omega is going to be Cauchy distribution. Okay? If you have Cauchy kernel, then corresponding distribution is Laplace distribution. There's some nice relationship between them. So comparing these type of random feature approximation approach to this low-rank matrix approximation approach, there's some advantage already. Okay. Essentially, what you do is you draw some random parameter omega, right? Random feature parameter, and then you're going to approximate this kernel function by the average of these random features. Okay? Instead of expectation, you just draw this omega randomly from p omega and approximate it by sinus sample average. And the computation is simpler. So just ignore the log d for the moment. Suppose you have a d there. Okay? Essentially, you just need to apply each one of these random feature function on each one of your data point. So if you have t random features, it's going to t times d for each data point. And you have n data point. That's the operation. So log d there is because we're going to exploit some tricks for efficient matrix vector modification and get log d kind of scaling. The memory is still order of n times t. Okay? So essentially, you can also build this matrix. Instead of using low-rank matrix factorization, you just compute, you apply this random function directly on your data point. You get a number for each one of these random feature. So again, once you have this low-rank factor A, you solve this t-dimensional problem. And again, if you want to prove something, you will find that the generalization ability is going to be 1 over square root t plus 1 over square root m. Again, you want to balance the two things. Yeah.
I'm missing something on the computation part.
Yeah.
even if I just want to write this approximate matrix,
Yeah.
so I'm not computing the true gram matrix,
Yeah.
I'm doing the approximation. Since it has size n by m, then it's going to take m squared.
Yeah, that's right. So you don't explicitly approximate the entry in this matrix. You just keep this lower factor A and work with this lower factor as if your data are from finite dimensional space or t dimension. So you're going to work with this, this matrix.
But my algorithm is going to access all the entries in the
Right. So your algorithm is
so in terms of the optimization algorithm, it's going to spend m squared on that regardless of what.
So before you run the optimization, you do this pre-processing. And that pre-processing actually don't need to access the entry in that matrix. You directly work with these data points. The same thing for this nice geometry in complete decomposition. You don't actually go through every entry in this matrix. Yeah, that's how you get the NT square. Otherwise, you can't avoid n square operations. Okay. You just use a few entries in this matrix to come up with the approximation. So in this case, you directly apply this random feature on your data points to get this representation, right? Okay. So again, you need to match the two. So yeah.
So how tight is this generalization bound? I imagine that your data lie in a low dimension space,
right.
and I don't. You might
Yeah. So in that case, you're lucky. This low rank approximation will work really nicely. And in that case, if you incorporate that low rank knowledge, you might get better bounds. In here, I'm not making an assumption about data. If you want to do something fully non-parametric, that's the kind of bound you will get. Yeah. So yeah. Okay. With the low-rank assumption, possibly you'll get better results. Okay. Better theoretical guarantee. Okay. That's the problem. And what I'm going to do is I'm going to look into some scalable algorithm, which has been applied in many other places, the stochastic gradient descent. Okay. But I'm going to add another layers of randomness to this algorithm to make it scalable for this kernel case. So first I'm going to show you is why traditional stochastic gradient descent is not good for kernel method. I'm going to directly optimize this function in the RKHS. I'm going to use something called the functional gradient instead of a gradient over some finite dimensional vector. Okay, it's just a generalization of that. So essentially, you perturb this function by some epsilon in the direction of g, and you look at the change. You can express that changes on inner products, and this thing in front of this g is going to be your functional gradient. For instance, if your function fx is here, you take a gradient with respect to this function. Then using the reproducing property in this space, you can express the function like this. Then when you take the gradient, it's like a linear function here, you get this term. If you have a square norm in the RKHS, you get the functional gradient like this, 2 times f. It's just, you think about it as a vector, then everything seems to be very natural. So essentially for this expected loss, okay, if you take the gradient, you apply chain rule once. You take the gradient of this loss function with respect to this fx and take gradient with respect to f again, you get this term here. You get this additional term here. And this comes from the square norm, okay? That's the, and then expectation can be exchanged with the operation of taking the gradient. So that's what you get. So essentially, for many of these kernel methods formulated as convex optimization, you can take gradient. It has form like this. And then what you can do is you take a subset of data points. You take one data point in this particular case, but you can take a mini batch. And then update your function using this stochastic gradient computed using individual data points. Okay? So essentially, in the end, you'll find that your function is a weighted combination of the data point you have seen so far, okay? And then the number of turns in this summation is going to be equal to the number of data points. So if you apply some standard analysis for stochastic gradient descent or mirror descent, and then you will get this type of rate, 1 over square root of t. In this case, the number of iteration is t. It's match up with the number of data points you see. So you get this rate, okay? But the problem of this approach is you need to remember all these training points. Okay? So you need to be able to, if you want to evaluate this function in a new test point, you have to keep all training points. Yeah. You plug in your new test point into this function, get the kernel value, and then do a weighted sum of them. You cannot throw away those training points in general. Yeah.
So is this t the same as t before the random sample of t points?
It's not exactly. I try to make them the same. So this t, you can think about it as the rank. Okay. It's not the same same parameter, but they're comparable in some sense. So the rank there, the t here, the iteration here, play the same role as rank in the previous slides. Yeah.
So I don't understand the comment. You need to remember all points. You just need to remember t points.
Yeah, that's right. You need to remember t points. So suppose you want to get 1 over square root m a generalization ability, then you need to essentially remember m points. Yeah. You need to remember the points you have seen so far. Yeah.
And also, where is the functional gradient? Can you go back to the functional gradient, which is perturbation of the direction of g?
Yeah, it's more like yeah.
Where did you use it here?
So essentially, I can actually plug in this into the buff equation, and then you can actually derive this result. For instance, you plug in this f here into this r, right? And then you plus epsilon g. And then you put it, you just look at the difference and then divide it by epsilon, you will get this. Yeah. So it's just like a, you can think about it just a vector. It's a vector.
Where is g here? So for this one,
yeah, the g is just here, but your direction of the derivative is just the part in front of g. It doesn't involve the g.
Yeah, I know. Yeah. So for here, I just imagine that's the part derivative.
Yeah, in here I just give you the final results. I didn't go through that step. I just give you the final result of taking this directional derivative. Yeah.
The directional derivative in the direction of which?
Yeah, in some g direction, but it doesn't matter. Usually for this simple function, that direction doesn't matter. Yeah.
I'm still trying to understand the red sentence in the next slide.
Yeah.
So you're saying that in order for I need to choose t to be on the order of m.
Yeah.
In the generalization I want.
Yeah.
But then the number of points that I need to remember is just the support. It's not going to be every.
Yeah. So for instance, for support vector motion, that's nice. You might get sparse solution. Some of the alpha are 0, and you can you
hope
can
if you choose the kernel correctly, it will be most of them will be 0.
So for support vector motion, that may happen, and then hopefully the orders of the number of support vector is orders of magnitude smaller than the actual data set. But for a ridge regression, for instance, usually the solution is dense, and for other many loss functions, the solution may be dense. Okay. So and also for support vector machine, generally there's no guarantee that the number of support vector is orders of magnitude smaller than the actual training points. Yeah. Especially for this highly nonlinear case, you'll find that you actually need lots of support vectors. Yeah. That's happening typically in practice. Yeah.
No, the number of support vectors usually grows linearly.
Linearly, right. So that if it's growing linearly, then that means the same order, right? So maybe the factor is small, but it's still linearly. Yeah. Okay. Right. So this is a key idea, okay? How do we deal with this problem of not remembering all these training points? So you just make a second stochastic approximation. So in stochastic gradient, you approximate gradient using data points. Now, I know this duality between kernel function and this random feature. I'm going to sample some random features. In this particular case, I just sample one, but you can sample mini batch as well. You're going to sample these random features and approximate this kernel function by these product of random functions. Okay. So the advantage of doing this is, of course, after you get this doubly stochastic gradient, you just move your function, update your function using this doubly stochastic gradient. And what you will find that the final function you get is a weighted combination of these random functions. You know exactly what form this function is, and then you only need to plug in your text x and evaluate that tax x on this random function, then and do a weighted combination, you will get your prediction. Okay? You don't need to remember all these points anymore. The reason why is you just need to incorporate the evaluation of this random function or these training points into these weights alpha. Okay? So in the end, this training data point, maybe it's 1 million dimension, but you just need to evaluate it in this random feature. And then it becomes a single number. It's incorporated into this single number. So if you go through 1 million data points, you just need to remember 1 million numbers, alpha. Okay? And then this random function, you know the form of it. You know which distribution you're sampling it from. Where typically we sample it from some pseudo-random number generator. If I know the seed, I can always re-instantiate that random number. Okay? I don't need to actually store this omega. I draw from my distribution. I just remember the seed. Next time, I would need to use that particular random feature. I'm going to redraw it, okay, using the same seed. So the algorithm is actually very simple. It's just keep updating, join some data points, join some random features, and keep updating this alpha. Okay? So the algorithm can be summarized in this one slide. In the end, the form of the function is going to be weighted combination of these random functions you have drawn. So essentially, you sample some data point, sample some random feature, using a particular seed corresponding to the iterations. Okay? Then you can re-instantiate this random feature very easily when in test time. In the current iteration, you already get a bunch of alpha. You already get a bunch of random feature. If you want to evaluate a new test point on this function you have, you just need to pass in the current set of alpha you get. So the evaluation of this function is going to re-instantiate a random feature and apply the random feature in this new test point and weighted by this alpha you learned before, and then you just accumulate this. Okay? And because the presence of regularization parameter, you see some modification of all these alpha j for j smaller equal to I. It's just because of regularization. You try to forget a little bit about the alpha you have run before. For the current alpha you're going to update, you just use this Doubly Stochastic gradient. Okay? Yeah.
So that reminds me of some feature generation process and signal processing, something like match and pursue or something. I forgot the name.
Yeah, so here is doing more naive than match and pursue. You are not doing smartly in terms of sampling this random feature. You're just doing it, drawing from some random distribution. You might choose some omega, maybe more smartly. You will get the better, maybe convergence. But yeah, I don't know how to do that.
Right, but then if you realize that alpha I is very close to zero, meaning that the random direction is orthogonal to the objective function, then maybe you can ignore that I. Is that the sound or correct?
It's yeah, it's possible. Here it's just we try to just explore the simplest version, and this one you don't do any big bookkeeping, and then you just keep averaging all these random functions. But you can think about the extension of this by drawing these random feature more intelligently, do bookkeeping more intelligently. Potentially, you can improve the convergence of this algorithm. Yeah.
I'm sorry, maybe I'm not following, but so are you describing to us the original technique of the random kitchen sinks of rectangular linear, or is this a new thing?
This is the new thing.
So
you don't generate.
Because to me, it's exactly what they said.
So what they did is they first generate this random feature, and then they optimize in the finite dimensional space.
Right, but you can do that optimization stochastically, which is what people will do in practice. Is that what you're saying?
So people don't do that in practice. People do that really generate maybe just 1,000 random features. You're optimizing this 1,000 dimensional space. And that's how people make it scalable for these kernel methods. And then if they want to try out more random features, what would they do is they regenerate another maybe 10,000 features and re-optimizing it. So this one is essentially generating this random feature on the fly.
So you're saying yours is more flexible?
In some sense, very flexible.
Not a problem how to make sure from the same omega, if you generate a feature from the flight, it's the same. If
Right,
you can take an omega, right?
So usually when we generate sample this, we use a program to sample this. And then you can always apply the seed to the random number generator. So that's why I need to keep track of the seed to make sure that every time I sample exactly the random. The question is, well, if you do something like this, is it going to converge? You have analysis for stochastic gradient descent. Now, you added this second randomness to your stochastic gradient. The question is whether it's going to converge, whether it's convergent to the same rate, with the same rate or not. Okay? So we also have some analysis whether this is convergent. And essentially, if you do this Doubly stochastic gradient, you will find that the rate of convergence is the same under some conditions. Okay? So the next thing, you actually need to remember this random field. What you actually remember in the algorithm are just these alphas. If you have 1 million data point, you just remember 1 million numbers. That's it. Okay? Yeah.
So I get confused. So I have one clarification question. So you can apply this technique to linear kernel, right? So if I apply this technique to the linear kernel problem with a lot of with data set with a lot of sparse features. So the process is I'm going to select randomly an example, then select randomly a feature.
Randomly a feature.
But then, in that case, many features will be 0 because if I do a sparse feature, then I just randomly pick a feature, every feature will be 0. Then the chance I get in update will be very low, right?
Yeah. If you do it, there's no advantage for doing this for linear features. Okay. And but the mapping of this algorithm to linear case exactly you sample these these dimensions uniformly at random. Because if a linear kernel, you just do inner product, right? It's a sum over the product of one dimensions and then the second dimension, third dimension. You can uniformly sample. Yes.
I think the problem for the linear feature is, in the linear case, you do not need to use the stochastic trick, because if you update for any feature, the partial derivative of any feature, you need to evaluate the inner product anyway, which gives you this number.
Right.
If you evaluate at the one, they simultaneously have for every feature. It's correct. You do not need to do
So I understand that probably there's better technique for linear. I'm just worried, in some case, maybe you need to sample a lot of times to go up.
Yeah, for linear kernel, I don't suggest using this approach. Yeah, this is really designed for nonlinear case. Yeah, exactly. Okay. Yeah.
That I don't understand. So the number of iterations. So in every iteration, you pick a new feature and you take a single sample point.
Yeah.
So if you generate 1,000 features, basically you observe only 1,000 points in your data set.
You can make these separate. So you can take a mini batch of data points. The mini batch can be different from the mini batch size of random features. Yeah. Okay.
So you just mentioned that you don't recommend this for linear and this for nonlinear. But actually, things between linear and nonlinear are not really that different. Say you can. So for your original data, you can just do like polynomial mapping and the hashing and
that's right, exactly.
Linear. So then you can still have.
So polynomial, I consider polynomial is already nonlinear. So actually, this random feature approximation for polynomial kernel, recently one very convenient technique is this tensor sketching. Exactly, you do some kind of random hashing, and then here you can think about this omega is performing some random hashing of your data. Okay. Again, you want to get the generalization bound. You will need the number of random hashing will have to match the number of data points you see. Okay? Otherwise, you're losing some performance without assuming any distribution for without any assumption of distribution of data. Okay? So the algorithm is just that simple. Okay? I mentioned about this random feature evaluation. You get log D instead of D. Because, for instance, for this translation invariant kernel, you have this random feature. Essentially, you draw some omega from some Gaussian distribution. You do an inner product between omega and x. If you have a bunch of random features, you have many of these omega drawn from distribution, and you want to evaluate essentially this. You put this omega in the matrix. You essentially want to perform the inner product between this W matrix and each one of your data point. Okay, so it's omega is a random matrix. Okay, the column is going to the row in this case, the column. Okay, the column is going to be some random number drawn from some distribution, for instance, Gaussian distribution, and you want to perform this inner product. So there's some way to perform this inner product in an efficient way. So essentially, this is some technique called fast food in machine learning. So you can approximate this matrix omega, W, okay, by several highly structured matrix. So you can actually have a product HG pi HB matrix. The B matrix is going to be diagonal matrix with the uniformly distributed, with the just entry -1, 1 on the diagonal. And then the probability of -1 and 1 are the same, okay? And then H is the Hadamard matrix, very structured. And this is, if your D is 2, is something like this, 4 is like this. So you don't actually need to compute these matrix. But the nice thing about this matrix, it allows you to do very fast matrix vector products. And then the pi is the random permutation matrix. And then G is just a diagonal of Gaussian. And then H is the Hadamard matrix again. So essentially, you don't actually need to draw these D times T random numbers from the distribution. So what you can do is you just draw this diagonal. Suppose T equal to D, okay? Diagonal of Gaussians. And you use these matrix, this very structured matrix, to mimic a huge random Gaussian matrix. You can do that. And then this matrix allows you to do fast matrix multiplication, and you can actually even provide guarantee that after you perform this approximation and do the matrix vector product, you get pretty much the same results. So this is some result from random matrix multiplication. And then you can actually use it here to speed up the evaluation of these random features on the data points, okay? So this is just some further speed up you can do.
And this is only really valuable for these translation invariant kernel?
So translation invariant kernel is this, for some other kernel, for instance, there's some rotation invariant kernel. You can also derive the similar thing, but it's not for every kernel, okay? So it has to be a kernel where you draw this omega from some distribution, maybe sub-Gaussian, and then multiply by these input data points and apply some nonlinear function afterwards. Then you will have these type of results. Okay. And then in terms of the convergence, we also provide some analysis for the convergence algorithm. Essentially, what we try to do is to find some function in the reproducing kernel Hilbert space. And then without making this Doubly Stochastic gradient approximation, the function we get is going to be something like this. Weighted sum of the kernel apply on each image chaining points. But we have to make some approximation, and then we get something like this, okay? So essentially, suppose you use this translation invariant kernel, then you're going to get a weighted sum of sine and cosine functions. These functions themselves may not actually be in the RKHS. You are actually using function in another space, approximate function in the RKHS. And you try to show the conversion. In here, we didn't show, we just showed that when you have that function, ft plus 1x, the function you obtain the t plus 1 iteration, and evaluate some point x, and compared to this f star function, which is in the RKHS, the best optimal function, evaluate x, the difference is going to be small. So essentially, you can decompose these differences into two terms. One, by introducing these singular stochastic kernel machine, okay? Just approximate with the stochastic gradient coming from the data, okay? So essentially, you can decompose the error into two terms. This decomposition is only expectation, by the way, okay? One source of error is due to this random feature. And then the second source of error is due to this random data. So essentially, for the analysis of it, we're going to analyze these two terms separately. So it turns out the second term, you can just use standard analysis from this mirror descent. You just generalize it to a function in RKHS. You can get this 1/t kind of convergence, okay? For the first term, we did something special to this problem. We use basically the concentration inequality for martingale differences. Essentially, if you compare this function in RKHS H and this function outside RKHS, the difference is this, okay? The difference is this, okay? It's a sum of a bunch of v's. Each v is just the function you obtain in each iteration. So somehow this sequence of v's form a martingale difference sequence, and you just apply some concentration inequality. It turns out you also get 1/t rate. Together, you get this kind of rate, 1/t rate for the function square, the square difference of the function. And then you can also get a generalization ability, which is 1 over square root t. Okay? So essentially, that's how you get this analysis working. And essentially, you get the best possible generalization ability for this non-parametric estimation problem. And the algorithm is very simple. Okay? The question is whether it works or not. So we tried this very, yeah.
Could you go back one please? Yeah. So H is what you would get
without applying this random feature.
A random feature. So yeah. This is what that is what the rectangular thing would do. Right?
H is not. H is this guy, which you don't apply any approximation to this kernel.
The actual kernel itself.
Yeah, actual kernel itself.
I see.
This F is applying stochastic gradient descent using random data, and also the random feature simultaneously. Okay. You never revisit those random features. You just keep generating new ones. Yeah.
I see. So the martingale is just
the difference.
Adding just doing the one by one.
Yeah, the difference is in on expectation 0. Okay, if you look at the difference between the two, so VI is this term. You have this using one random feature, you try to approximate this kernel. Okay, conditioning all the previous randomness, the expectation of this guy compared to this guy is 0, because this kernel function on expectation, this random feature approximate on expectation is equal to that. Yeah. So conditioning all previous randomness, because we have the previous function here, this expectation is 0. And then essentially, if you look at the difference, it's the sum of a bunch of this. Okay? So
why is everything squared there? Why is the difference between FT plus
so we just consider the square difference and then take the expectation for it. So this decomposition is in terms of expectation. Yeah. We just look at the square difference between the function value. It's easier to analyze. You look at the absolute difference as well. Yeah. But we just look at the square difference. Okay. And then the second part is just linear descent. Okay. And then if you have some property for loss function, then you get this kind of rate for the risk expected loss.
And what is this kappa or this k? What is that thing over there? This constant? What is that? Or some k? This 2k.
This k.
And up on the top there.
Oh, kappa is parameter related to the kernel function. It's like upper bound for the kernel function. For instance, you have RBF kernel, then that's one. Essentially, there is using the reproducing property. You can express the evaluation of a function RKHs as inner product between, for instance, H and KXT, and then you use Cauchy-Schwarz. That's how you get the kappa. Yeah. So we're going to apply this algorithm to this very challenging data set. You need to go to maybe 10 million or even more data points in order to get a state-of-the-art performance. So we compared 3 models. Okay, one model we call jointly trained neural nets is the original neural nets. We're going to use stochastic gradient descent and manually adjust the learning rate 3 times to get the best performance. And then we're going to have the second model called fixed neural net. It's basically a sanity check. So we're going to take these convolution layer learned by in the first model and fix it here. I'm just going to retrain again, just these fully connected nonlinear units and multi-class classification. Okay? And in some sense, this model is the closest to our model. We are also going to reuse exactly the convolution layer learned by the neural nets, but we're going to replace the top part by this kernel machine. Okay, so it seems that this convolution pooling is really doing something amazing. Okay, so we're going to replace that and use this Doubly Stochastic kernel machine. Okay.
Good question. Why don't you also do the joint?
So it's not a convex problem anymore. If you want to also optimize,
it's like it was a convex problem.
It's
not like the first one is a convex problem either.
Yeah, that's right. So actually, we have tried. I will tell you the result. Okay, but at the moment, I'm just focusing on like replacing this part by this kernel machine, which you have a very nice guarantee, and then see whether it performs well in practice or not. Okay, so this is the previous figure you have seen. That's for training these deep neural nets. And then if you train these fixed neural nets, you have already learned this convolution layer, right? You just try to optimize the top fully connected layer, and then you get this. Somehow you don't get the best performance comparing to these, yeah.
Using, sorry, using all the same tricks of doing manual intervention.
Yeah, this one is not. So you just have, yes, that's right. This one, yes, you have adjusted. But somehow at this point, it's, even you adjust it, it's not decreasing anymore. Somehow there's some co-adaptation of the convolution layer and then the fully connected layer. Somehow you train it jointly, you get a better model. But if you fix one point and train the other one, it seems that you're not getting as good a result. It's still, here you are still trying to optimize some kind of non-convex objective function. We don't understand very well why this is the case. Yeah. But if you use this doubly stochastic kernel machine, that's what you get. You have faster convergence, and then you just use 1/t type of learning rates. Okay, that's what you get. Yeah.
Do you have also this graph in terms of time?
The time is this is 1 week, and the time is comparable to these neural nets.
So the iteration time is comparable.
Yeah, comparable. We also implement our algorithm in GPU as well. It's comparable. Yeah. So actually, most of the time is spent on loading the data and then performing transformation and convolution. So although this convolution only has 3 million parameters, it actually performs most of the computation. And then these 60 million parameters later, it's only taking fractional time.
But you only have to go through once.
No, not once. Yeah, for us, we can also go through a data point many times because every time you don't see exactly the same example, and then you actually make a random cropping of this image and then random mirror imaging and some transformations. In some sense, you never see the same data point.
Oh, okay.
Yeah.
So why does the red line end sooner?
So we didn't, it's not improving anymore. It's not improving anymore. That's why we just.
How do you know? Did you go to
So we go to some, I think we go to some longer thing and it doesn't. Yeah.
So it stops at 10 times less data than the green line.
Yeah.
So if the green line takes a week and you are at the same speed.
No, so I mean, at this point it's a week. The student is not patient enough to wait for.
But you're using the results of the green line generated for the
the convolution.
Convolution thing.
So how much does just your training of the?
So a few days as well. It takes a few days as well. So I don't remember exact time, but it takes a few days. So it's that most of the time is actually loading the data and doing all this convolution thing. So because our method is something new, the student is not sure whether this method will work or not. He tried many different things for this, some constant in the learning rate, and he didn't wait for 1 week for each one of these experiments.
What's the dimension of the inputs of your system?
The dimension of these input, essentially this one, right? This layer, it's like 6,000 dimension, around 6,000 dimension. Yeah.
But I think if you say like 1.3 million in 1,000 classes, then even if you just use the traditional kernel learning, just to train it, I think it can also be done in probably several days.
Possible. Hopefully someone can try it, and that means that we really haven't tried hard enough kernel method. Okay. Actually, in this case, we need 10 million or more, okay, to get a state of art. It's still decaying, okay? You need to go to that kind of scale in order to get a state of art performance. Yeah.
But using your 1.3 million,
yeah.
So how is it related to number?
I see. So the original image is 1.3 million, but as I mentioned, you generate this virtual image, right? You take the original image, you crop it, and then flip it, and then do some transformation, yeah. And you generate slightly variation of the original image.
Then with so many samples, you cannot do the traditional.
Yeah, that's right. It's harder. Maybe you can wait longer or use a larger machine, but for a typical, desktop, it's difficult. Yeah. Okay. It's difficult. So you get this. We also tried some other data set that the story are pretty much the same. For CIFAR-10, you also generate virtual image. That's why the data point can go up to 10 million. Okay. So this kernel machine converge much faster, and then you get about the same performance in this case. The data set is simpler. It's only 10 classes. So we actually get the same performance as neural nets. So you can also look at this even easier data set.
Can you go back for a second? So here you get a different picture from before, which is the fixed neural net actually performed better than the jointly trained.
Right. Right.
So could it be that is the difference statistically significant? Can you analyze something like that?
We didn't. It's taking quite a long time. We just look at this test error, and that's if we run several times, probably we can average a curve, and it's maybe not significantly different. The data set is simpler, and then what I can say is they pretty much get the same performance. Okay, and in this case, I believe we didn't adjust the learning rates. Yeah. Yeah.
Maybe I missed something earlier. So what is the loss function that you use in the doubly stochastic group?
It's a multi-class logistic regression. Yeah. Multi-class logistic, the same thing for neural nets.
Exactly the same.
Yeah, right. And MNIST digit, that's even simpler, right? And then you can actually also make some small transformation of the image. You can generate up to 8 million data points. And in this case, error method gets very small error. In this case, below 1%. Okay. So for instance, I'm slightly faster, but I cannot say statistically whether it's significant or not. This one is fast because the image is small, and then the neural net is only actually 2 layers. So it's not every model is this 7 layers. This is for ImageNet. For the simpler data set, you actually use fewer layers. This is 2 or 3 layers. And then the images are also much smaller. And this one is within a day, very fast. You get similar type of results. And we also have tried regression problem, not just classification problem. In this case, we tried something like trying to take some 3-dimensional structure, this molecule, and predict some property of this molecule. For instance, how efficient this molecule is converting sunlight to energy, things like this. And then in order to do that, you had to first represent this kind of 3-dimensional structure, some feature representation. Okay? So people have already come up with some permutation invariant feature, because in this case, it's a 3-dimensional structure. You have the coordinates, you rotate it, you get different coordinates, but it's the same molecule. You need some way to represent this thing. They come up with something called the column matrix, looking at the pairwise charge and then divided by the distance, and then you get this matrix, you permute it as your data points. It's a regression problem. The output is between the range of 0 to 12. And it's just a regression problem. You don't use this convolution pooling anymore. Okay? In this case, it's really just fully connected neural nets for 3 layers. And then we just do this kernel ridge regression. Okay? So this is just comparing the fully connected network to kernel machine. Okay? So in this case, we go through this 2.3 million one and look at these basically the mean absolute error, okay, in the test set. And in this case, you see fewer points, actually. The reason why this curve is so smooth, we have a fewer points for the evaluation, and then MATLAB just interpolate. It feels like smoother, okay?
So have you tried to compare your method to the traditional?
Yeah, so in the paper, yes, we have. We compared to this dual coordinate descent, things like this, on UCI data set, where we can actually run the competitor. So in that case, essentially, what we show is the convergence rate is about the same. Okay, we are not clearly better than other methods in terms of rate of convergence and then the final classification accuracy. It's just that our method is more scalable, allowing us to try out this type of data set. Okay, so what we find is this fully connected layer, and the neural nets is really not useful. Okay, you can replace it by other kernel method, non-parametric method. You get about the same performance. What seems to be really useful are these convolution and pooling layers. So what we tried is exactly, we're also going to learn 2 things together. We're going to learn this kernel method classifier and also simultaneously adapting these convolution layers. So just by chain rule derivative, okay? And then what you get is you can also get close to the performance neural nets. We just tried it recently. We get 46. For neural nets, you get 42. Okay, there's still gap, but this is much better than random guess. Random guess is 99.9 something % error. Okay.
So is this better than doing this separate thing that you mentioned before?
It's about the same. Okay. Yeah. Separate thing, you already learn is filters, right? That's much easier problem. You just learn to classify. Here, you simultaneously learn the filter. That we don't have any guarantee for this, but somehow works, okay? You don't need to use these fully connected and rectify linear units. You put conversion here, you adjust this, it somehow works, yeah? We didn't tune it extensively. We could possibly get even better results.
So here you still have the convolution layers. Yeah. You just learn you do the back propagation from
exactly. the kernel
method.
Yeah, exactly. Right. Okay.
So if you use the phased convolution, then from neural networks, and then what was the error rate here?
So for it's like a 44.
Oh, 44.
Yeah. And then we just tried it in a few months, and that's the result. It can improve. Okay. Essentially, with this, I'd like to summarize a little bit. The method that we scalar this. We used to scalar this kernel machines really just this one slice. Instead of using the training data, random batch of training data, you also use a random batch of random features simultaneously to approximate this gradient, and using this doubly stochastic gradient to update your function. In the end, your function is going to be weighted sum of this random feature. That's the same representation as this random kitchen sink. But the way we use this random feature is different, okay? We generate this random feature online, and we never revisit them, okay? But in practice, you can revisit them, okay? You can blend between the two. Okay? So the advantage of this approach is you can actually use it to handle streaming data. Suppose your data is just keep streaming in, right? You can just keep increasing the random feature to accommodate this increasing complexity of the data. Of course, there's also interesting problem of what if some data or classes you will never see in the future, you want to forget about it. How do you do it nicely, such that you keep the overall representation still manageable, for instance? So it can be applied to, of course, this convex objective function, but we also recently trying it for kernel PCA. Okay, for principal component analysis, you solve some kind of non-convex problem. You try to maximize a convex function instead of minimizing it. You can also use this stochastic gradient to do it, and then it doesn't prevent you to use the doubly stochastic gradient. You can actually also provide the guarantee for this convergence if your initialization is close enough to this basing of a tractor. Okay, Gaussian process, you want to estimate the predictive mean and covariance. It can be set up as some convex optimization problem. You can also use this approach. So in memory-wise, we just need to remember this alpha, one for each data point. So that's why it's OT if you run T iterations. And in terms of estimating the function, we get this rate. In terms of the generalization ability, we get 1 over square root T, okay? That's the best possible for this kind of non-parametric method without further assumption. In practice, it also works nicely, okay? That's the most important thing in some sense. So there are many other questions that hasn't been resolved. So at the moment, I'm also looking into these two questions on the top. So what is maximum pooling and convolution is actually doing, okay? Why can't we use other architectures, yeah, and to get about the same performance? So people have go to extreme that you're not just having 5 layer of this, you might have a 15 layer or maybe 20 layer of this, and very small convolution kernel, and you get even better model. So it's amazing. You can do this. And you get some model close to human judgment. And then if this architecture works, it must be some characteristic of the data which is suitable for that type of operations. If you apply this architecture to other domain, maybe language, it's not going to work, okay? There must be some characteristic of data. What kind of characteristic is there, yeah, to make this architecture work? It's not clear. We are studying this. Hopefully we can get some result in future. If I come back, I will give this talk. Okay, that's everything. Okay. Any question? Yeah. Further question?
Okay, from the previous slide.
Yeah.
Okay, this slide. So this is from the actually function estimation or you see optimization perspective, you get the same convergence rates as the single stochastic rate, right?
Yeah.
So the question is, in practice, do you observe more variance?
Variance, yes, you have more variance. Essentially, the variance add up. in the bound.
And also, even from the theoretical result, you got the same rate in terms of t, but the constant is that can be much larger.
Yeah, it's going to be larger, exactly. You have two sources of variance, one source from the data, another source from the random feature, exactly. So it is convex optimization, remember? In practice, you will try to grab as large mini batch as possible and generate as large batch of random features as possible, as much as your memory can hold and do this. You don't actually just use one data point. It's actually interesting that it's different for neural nets. Somehow, in order to make these neural nets work, you have to use a mini batch that is small enough, not too small, not too large, a few hundred points or something, in order to see the best convergence for neural nets. It's a non-convex problem. Somehow, there's the best stochasticity that allows you to get a better result. But here is a convex optimization. You really want to have as little randomness as possible. Yeah. So we will grab a large batch, mini batch. Yeah. Right. Any other questions? I will be here for a few days. If you guys are free, I'd be love to talk to you guys more. Okay.